All right, I'm ready to get started. Greg, are you? All right. Let's see if I can do this. Oh boy. Live from Earth, it's Space Radio. This is Paul Sutter, and coming up, we're talking about redefining planets yet again, but not in the way you might think. And if I have time, talking about how nobody wins the moon this time. And of course, taking listener questions about all things, well, all things, because this show is about the entire universe. We record the show every Thursday at 4 p.m. Eastern, so call 888-581-0708 to join the conversation. And in today's Blue Shift, I'll be talking about a different kind of science communication. But first, the news. Hello, space fans. Welcome to Space Radio. I'm Paul Sutter, astrophysicist at Ohio State, chief scientist at COSI, and for the next half hour, your agent of the stars. We've got an exciting show for you today on Space Radio where we talk about all things space, astronomy, astrophysics, rocketry. If it's above the Earth's atmosphere, it's in this show's universe. This show lives on listener questions. We record every Thursday at 4 p.m. Eastern here in Studio A of WCBE Radio Columbus. So call 888-581-0708, light it up. Get those calls in and we'll have a lovely chat about science. You can also follow along on our live streams on YouTube, Facebook, and Twitch. Check out spaceradioshow.com for the links. You can also follow me directly on social media. My name is at Paul Matt Sutter. Seriously, folks, I've only prepped 10 minutes of show material tops, and it shows, so get those calls in. All right, we've got another caller, Greg, so I'm going to screen that caller. And I don't remember okay, it's this one. Hey there, number ending in 8041. How's it going? All right, so normally we have our producer, Greg, screen the calls, but we're having some technical issues. So I'm getting your name and a quick version of your question now, and then I'll return to you when I get to that part of the show. So what's your name and what's a quick version of your question? Oh, very cool. That is lovely. Now I'm going to put you back in the queue. You should be able to hear the show. Just stay on the line and I'll get to you in about 5 minutes. All right, sounds good. Thanks, Randy. Okay. All right, do the news segment. Who needs you, Greg? This is easy. Before I start taking calls, though, I want to share some interesting bits of news I caught recently. And it comes up like every other day, this whole discussion about Pluto, of whether planets like Pluto or objects like Pluto, sorry, revealed a little bit of my own bias there, if objects like Pluto ought to be classified as planets or dwarf planets or who cares or whatever. And that's a very interesting discussion that relates to our evolving knowledge of the solar system, especially the outer solar system, especially the formation of the solar system. But that's kind of on the low end. Like these small objects that are scattered around the system, what should we call them? Do they qualify as a planet or not? But there's also a parallel debate happening at the opposite side of the size spectrum. How do you define a star versus an object called a brown dwarf, which is like a failed star, versus a planet proper? Well, I think the easiest thing, a star is easy. If there's nuclear fusion happening in the core, boom, you're a star. And there's a certain mass threshold you have to reach, about 20 to 100 times more massive than Jupiter, before you have enough intense gravitational pressures in the core to ignite nuclear fusion, and then boom, you get to be a star. If you're less than that, if you're really, really, really big, but no nuclear fusion, you're not quite ready for prime time, then you're called a brown dwarf. And then if you're smaller than that, you're called a planet. What is the difference? Where is the line between a really, really, really big planet and a failed star? And some recent research recently published in the Astrophysical Journal by Johns Hopkins University researcher Kevin Schlafman suggests that nature is providing a convenient dividing line between planet and brown dwarf. And he did this analysis of a bunch of known brown dwarfs and a bunch of known giant planets. And there seems to be a relationship where if you're less than around 10 times more massive than Jupiter, you tend to form around like a planet where a star formed, had an accretion disk left over, little nuggets started collecting themselves and building themselves up to become a giant planet. But if you're over 10 times the mass of Jupiter, you seem to form, or evidence suggests that you form in a different way from the catastrophic collapse of a cloud of gas, the same way you would form a star, but just not enough gas got together to actually trigger nuclear fusion. And so that could be a convenient dividing line between what we call a planet and what we call a brown dwarf. What does this have to do with Pluto? Absolutely nothing, because it's on the opposite end of the scale. But it's another example of how we're continuously having these kinds of discussions. We're constantly checking back on ourselves, revisiting ourselves to see if the definitions we came up with decades, or in some cases centuries or millennia ago, still hold true with all of our new accumulated knowledge, because that is exactly how science works, and that is one of the reasons that make it awesome. You're listening to Space Radio. Remember to call 888-581-0708 to talk. And that's the latest and greatest when it comes to news. Let's have a conversation. All right. I think I did this right. Randy, you should be on the line. Can you hear me just fine? All right. So, okay, perfect. So what I'm going to do is I'm going to introduce the segment, and I'll introduce you, and then we'll start our little conversation. All right. We've got a caller. Hey, Randy, thanks for calling Space Radio. Where on earth are you? Sarasota, Florida. Sunny Sarasota, Florida. What are you curious about today? Any day now. Any day now. I swear it. The James Webb will launch. Yes. Shh. Oh, that is such a good question. Thank you, Randy. The James Webb Space Telescope is the next NASA flagship mission. It's going to be a gigantic telescope. It's, like you mentioned, it's going to be far away from the Earth. It's not in orbit around the Earth like the Hubble is. It's going to be very far away from the Earth, which means we get something messes up on that instrument, like something messed up with the Hubble. That's it. We've blown how much did it cost? Hundreds of millions of dollars? We've blown it all. So that's why there's so many cost overruns, there's so many delays, because we absolutely have to get this right. There is zero margin for error. Now, in terms of the science, this isn't just a case of, hey guys, let's just build a giant space telescope and hope we see something cool. In order to get funding from NASA, in order to get funding from the government, we actually had to provide, that we being the astronomical community, we had to provide a case. We had to justify, hey, taxpayer, why don't you give us tens or hundreds of millions of dollars, and here's what we expect to find. So I'll tell you what the James Webb hopes to achieve. Number one, the James Webb Space Telescope is not designed to deliver pretty pictures like you think like a successor to the Hubble will. It's called the successor to the Hubble. The Hubble sees light in the same visible spectrum that humans do, so it produces all these wonderful pictures. The James Webb Space Telescope is going to be a mostly infrared telescope. It's going to look below the visible. And the reason it's doing this is because it's looking very, very far out into the universe. So far out that the expansion of the universe from the time that the light was emitted from these distant galaxies, the distant stars that it's going to target, since that time, the expansion of the universe has stretched out light to go from the visible down into the infrared. So the James Webb Space Telescope is specifically designed to hunt for the first generation of stars, to hunt for the first generation of galaxies, to appear in our universe over 13 billion years ago. That is one mission. Another mission is it is going to be an exoplanet hunter. It is designed to watch the motions of stars and hunt for planets around those stars and try, maybe, get a hint of the atmospheric characteristics of those planets, hunting for life. Another mission of the James Webb Space Telescope, because it's such a good infrared telescope, is to look at stellar nurseries in our own galaxy, to look at baby stars, baby solar systems, see how these things are formed. Usually these kinds of systems are cloaked in thick layers of dust where you can't see anything with your eyes, but infrared light sails right through so we can get a hint. So the James Webb is hunting for old things, it's hunting for new things, and it's hunting for life. How long that will take to get? The James Webb has a design lifetime of, I think, a decade, between 5 and 10 years. I'm not 100% sure on that number, but it's somewhere in that ballpark. It will take a few months of just testing, of calibrating, of making sure we understand how this instrument works now that it's actually in space and actually operating. We'll start seeing interesting results probably within a year. Within a year, we're starting various teams that are using this instrument, do their targeting, do their observations, produce the data, write the papers, and publish them. So start looking for some really cool stuff a year after it flies. And when it flies, that is a continuing and evolving process, which is the most diplomatic way I could think of it. Did that satisfy your James Webb curiosity? Yeah, I'm glad it did. Thank you so much for calling, Randy. It was great to talk to you. Great question about the future of space missions. Remember, you can call 888-581-0708 and join the conversation, or catch the live streams on YouTube, Facebook, and Twitch. Visit spaceradioshow.com for all the links. I'm Paul Sutter. This is Space Radio, and this show is brought to you by you. Visit patreon.com/PMSutter to learn how you can keep this show on the air. See you after the break. All right, so I know there's some more people in the screening queue. Let me see. I think Jack dropped off, but he may have called again, so let me see. Caller 2662, how's it going? Okay, you're Jack. Okay, so I'm gonna put you back on the queue, and then we've got a third caller that I'm gonna go talk to them for just a quick second. All right, so we've got Jack. He's on line 2662, and then we've got 8063. How's it going? Ryan, nice to meet you. What's a quick version of your question? Good question. I love that question. I love that question. So normally Greg, our producer, is screening calls, but we're having some technical issues. So that's why I'm talking to you a little bit ahead of time. You got a great question. I'm going to put you back in the queue so you can hear the show, and I'll get to you after I talk to Jack, so in about 5 minutes. All right, so just stay on the line. All right, I'm going to handle these two callers. Sorry, live streamers, lots of calls. You guys, you should have called. Are they going nuts? I haven't even followed. Okay, the live streamers are amusing themselves, as I suspected they would. All right. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got another listener question ready to go, but remember, you can join the conversation by calling 888-581-0708 or by following the live streams. Check out spaceradioshow.com for all the links. We've got Jack on the line. Jack, where on earth are you? Jack, are you there? Earth to Jack. Space Radio to Jack. All right, sorry, Jack. I'm going to put you back in the queue, and we might be able to come back to you. Greg, should I just restart the segment with the other caller? Yeah. And then I'll take a question from the live stream. We'll talk about Neptune's dark spot. Okay, good. So, Ryan, you're going to come up. Welcome. Sorry, Ryan. I'm going to start the segment and then I'll bring you on. Welcome back, everyone. I'm Paul Sutter, and this is Space Radio. We've got another listener question ready to go, but remember, you can join the conversation by calling 888-581-0708 or by following the live streams. Check out spaceradioshow.com for all the links. We've got Ryan on the line. Ryan, where on earth are you? All right, a repeat caller. I love this. Ryan, this is so exciting. What is your question? This is an excellent question. I love this because it touches on so many things that are happening inside of the interiors of brown dwarfs and stars. First off, the brown dwarf, it's kind of a really lame name that doesn't do the object justice. Yeah, they would look kind of vaguely brownish to the eyes, but they're actually really warm. I mean, you've got a giant thing that has collapsed into a small amount of volume, that's going to release a lot of heat and that's going to retain a lot of heat for a long time. So these brown dwarfs are very strong in the infrared, and they do sometimes glow a little bit in the visible depending on how recently they formed. So this is actually how we spot them. We do surveys in infrared light, and they're like little hotspots blinking all around. Now I'm going to change to a slightly different topic to illustrate the point of what happens in the interior of a giant object like a brown dwarf or a star, and how changes in the center propagate outwards. You're absolutely right that when a bit of light, a photon, is generated from the nucleus in the core of our sun, it takes somewhere around 100,000 years to hit the surface of the sun, and it's released into space, and then it goes and gives us sunburns and everything. And so that's about 100,000 years. Let's say, just for fun, that tomorrow the nuclear reactions in the core of the sun shut off. Just shut off, no more. No more nuclear reactions in the sun. You can ask, and this is a astronomy graduate level homework problem, maybe even undergraduate level, how long would it take for the surface of the sun to change? How long would it take for the rest of the sun to notice? And the answer is really surprising. It's somewhere around 100 million years. If you shut off energy production in our sun right now, it would take 100 million years before the surface of the sun would have anything visibly different going on. And the same thing happens in reverse with a brown dwarf. If it's accumulating matter, if more and more gas is piling on, and finally the core reaches the critical temperatures and pressures to trigger nuclear fusion, and like, ba-ba, the party starts, it's gonna take potentially hundreds of millions of years before the surface of that brown dwarf visibly changes and we would recognize it as a star. It's not like a switch would flip on, like we're staring and staring and staring, and then, oh, it's a star. It would gradually transform itself over the course of 100 million years or so until it was visibly like a star. I hope that answered your question. Did that satisfy you? Right, that is a very good question. And that is your intuition would lead you to think, like, oh, if suddenly there's a giant source of energy in the core of this brown dwarf, it's going to immediately ripple outwards. You know, there'll be expansion effects because there'll be a source of pressure. It will heat up, etc., etc. But the physics are actually a lot more complicated because we're dealing with something that is very unfamiliar. We're dealing with giant objects. And giant objects don't necessarily behave the way we expect them to. Yes, the interior, the core, might have nuclear fusion triggered, start generating energy, but because of all the incredible pressures, because that object is already really big and really hot, and hot gases have, that's not going to be as dramatic a shift as you might think once that critical threshold is reached. So there you go. I think the big lesson here is big objects do not behave the same way. Thank you so much for calling, Ryan, and I hope you're satisfied because I'm done talking to you, because I want to get to another question. This is actually a question that popped up on the live stream, and a lovely little discussion happening on the live stream right now as I talk about dark spots on Neptune. Now, we're all familiar, I hope so, with the Great Red Spot on Jupiter, the giant hurricane that's twice the size of the planet Earth that's been raging for hundreds of years. Jupiter's not alone when it comes to giant storms. Saturn has giant storms, Uranus has giant storms, and Neptune has giant storms. And when the Voyager probes blasted by Neptune and saw these dark spots, it spotted some storms. And then we've done follow-up observations with the Hubble. And these storms, unlike the Great Red Spot on Jupiter, have gone away. They faded away with time. And then starting a couple years ago, some more dark spots appeared. So what are we seeing? We are seeing active storm systems on the outermost layers of these giant planets. And what's fascinating is these things are big. These storms are big, like the size of a continent or bigger. Definitely bigger than a hurricane on Earth. They're giant. They're forming over this time of months. They blow for a few years, maybe a couple decades, and then they die back down. This is telling us some interesting things. It's telling us that the interiors of these giant worlds are incredibly complex. That they are as interesting, if not more so, than the atmosphere dynamics of the Earth itself. Even though they're so far from the sun, even though they're plunged in perpetual twilight, even though they have droplets of frozen methane and ammonia, even though their moons are locked in ice, even though the energy scales are so much lower because they're so far removed from the sun, they're not heated, they're not warmed by the sun, they have complex, fascinating interior structures, and we don't know a lot about them. The Voyager missions were the only missions to visit Uranus and Neptune. And what we got from that is basically what we got when it comes to close-up measurements. We do have remote measurements, we have telescopic observations, but when it comes to the close-up pictures and information, the same way we know a lot about Jupiter and Saturn and now even Pluto, we don't know a lot about Uranus and Neptune. And we're not going to know a lot for a while because no missions are on the slate. Thank you so much to the amazing questions today, both calling in. Sorry, I know we've got more callers. Try again next week. The lines will be open again. And of course, the always lovely live streamers. I've only had to delete and ban a few of you today, so I really thank you for that. We're almost out of time on Space Radio, but before we go, it's time for the Blue Shift. I'm Paul Sutter, and you're listening to Space Radio, and this is the Blue Shift, my opportunity to get a little bit closer to you. And I've received a few comments recently, some negative, some positive, about my style, my tone, my approach to science communication. And yes, I'm very incredibly grateful that there have been a lot of supporters for this show and the other shows I do, both online and on the air here on WCBE, and I'm eternally grateful for that. I also receive criticism, fair enough. I know I'm an acquired taste when it comes to science communication. But what I want to tell you in the next couple minutes is that you better get used to that. And I'm not speaking egotistically. I'm not speaking like, oh, I'm going to be super famous and I'm going to saturate the airwaves and TV and media when it comes to science communication. That's not what I'm trying to say at all. What I'm trying to say is that the future is going, when it comes to science communication and how people popularize and communicate science, is going to look vastly different than the world of 10 years ago or 20 years ago, and it will look vastly different than the world of today. Look at a show like How the Universe Works on Science Channel, which I'm very lucky to be a part of, where each episode features half a dozen scientists. Each of those scientists are incredibly enthusiastic, incredibly passionate about what they know, and they love to share it. They each have different voices. They each have different attitudes and personalities and approaches, and no scientist is necessarily guaranteed to become big like Neil Tyson or Bill Nye or that level of celebrity. But that's a very, very good thing because we live in an age of the democratization of media where we have half a dozen social platforms that are all huge. We have YouTube, which is huge. We have radio, which is still awesome thanks to your support. We have TV. And everyone can find their niches and express themselves, where we're breaking down barriers between scientists and the public, where scientists don't have to go through intermediaries like press officers or journalists to talk to people who are interested in what they do. And because of the breakdown of the barriers, you're going to hear more raw science from actual scientists. So not just me, but in all sorts of fields, of real people who are flawed, but have their own personalities and their own quirks and their own ways of expressing themselves, but they all share something in common. They're all incredibly passionate about it, and they're going to talk directly to you. So I think that is what the future is, and I'm so excited to be a part of it, that not just me, but scientists around the world get to share directly, warts and all, with you. And unfortunately, this broadcast is almost done. Thank you for joining me on this voyage of Space Radio. Once again, I'm Paul Sutter, and this show is brought to you by the Ohio State University Department of Astronomy. Learn more at astronomy.osu.edu. The show is also brought to you by you. Visit patreon.com/pmsutter to learn how you can contribute. Thanks to Greg Moebius for producing, Dan Michalko for being awesome, and all the fine crew at WCBE Radio for making this show possible. We record every Thursday at 4 p.m. Eastern. Call 888-511-0708 to join me on the air. Also, you can catch the live and also follow me directly on social media. My handle on all platforms is @PaulMattSutter. Go to spaceradioshow.com for all the info. And of course, thanks again, Earthlings, for listening. See you next week. And remember, science is for sharing. End of transmission. We made it. We did it, Greg. I love Paul Stiles, even though he is like MST3K. Larry, MST3K, I grew up on MST3K. I remember my first episode, July 10th, 1993. The first time I caught MST3K. I've been watching it ever since. And that is where I get all of my sensibilities when it comes to communication, when it comes to oh my gosh, like you should seriously see me on How the Universe Works, because they kept all the wisecracks. They kept all the jokes. They kept all the times I was trying to make myself laugh and make the producers laugh. And they kept it all, which is hilarious. They also added in the bits where I was actually explaining science in a very serious way. But it's hilarious. If by the way, guys, if you can catch the premiere episode each night, Tuesday at 10 on 10 p.m. Eastern on the Science Channel, I'm live tweeting, kind of making fun of myself for doing all these wisecracks. So feel free to join me on Twitter as I live tweet those shows. And thanks again, live streamers. I know the technology is not where we wanted it today. Thanks for playing along. And I know this doesn't look the greatest. Thanks for watching. I love all the conversation we had. And I'll talk to you next week. Oh, but what should we call today's show? Put some ideas in the comments. I can see the comments. Feel free to toss out some names for today's show. Suggestions. I title every single episode based on your suggestion. Oh, wrong island. That's the infrared telescope in the Brown Dwarfs, Neptune's dark spot. Very descriptive, Jonathan H. Let me kill all my lights. I'm going to let you guys simmer on that. I'm going to let you guys cook on stars and plunots. Cheese grind. Now, Michael, you know I have a thing for cheese. We cannot put cheese in every single title. That might get a little bit weird, even though my heart and my stomach is telling me to do exactly that. Amir, how about answering some questions here? Usually, if you come on before the show starts, in that 15-minute window before we go live with the show, I'll be chatting with you guys. Don't worry about that. Phone improvised space. What do you think, Greg? Phone improvised space. Michael, I know you owe me some cheese. It's okay. I'm patient. I'm a patient guy. One-sided conversation. Very large objects. I think that's it. With an exclamation point. Very large objects. Ryan. That's it. I love that. Just straight up, very large objects. Are you the same Ryan that called in? Or are you a different Ryan? Do we have more than one Ryan following this show? Is there cheese on Mars? No. I wish. Then I would go. Yes, Catwow, I know you couldn't hear the callers. That's because we had a different setup today. Our main computer that normally is able to route the audio to the live stream was down because it wanted to update in the middle right before we went live. So you're just watching on my phone. So I'm very sorry about that. I know you couldn't hear the callers. And try again next week and hopefully we can fix that. All right, I'm doing it. Very large objects with the exclamation point. Thank you so much, guys. I'm going to turn this off, and I'll see you again next week. Yeah, Vulcan salute. Right there.